This material is from chapter 8. We're going to talk about metabolism and the energy of life. So we want to take a look at some basics of energy and then how that moves through your system. So we'll start with some of the basic energy definitions and go from there. And so first of all, metabolic pathways, that's pretty much all the chemical processes in your body. And so what we have is really two types of pathways. We have the anabolic pathway and the catabolic pathway. And so anabolic pathway means to build. And so last when we were talking about steroids, steroids are anabolic steroids. That means to build. And actually anabolic steroids were designed to build muscle, and that's what it does, although there are major side effects like shrinking testicles and acne and kidney damage, cancer, those kinds of things. But so anyway, anabolic means to build. And then we have catabolic pathways, and catabolic actually means the opposite, which means to break down. So both of these combined will pretty much make up the metabolism in your system. All right, and then there's two forms of energy that we want you to know. The one is kinetic energy, and then the other is potential. So here we have a picture of kinetic energy, and that is the energy of motion or movement. And so you can see that that is water coming out of the dam here. So that would be an example of energy of motion, energy of movement. Yeah. And that's where you have this. Now, thermal energy is actually also an example of kinetic energy, and within atoms, again, they're not static. Electrons are moving, and when we transfer this energy from one object to another, we call that heat, and that's how we measure heat. All right, the next one is potential energy, and potential means stored or energy of position. And so chemical energy. So in this scenario here, this picture, the gasoline would actually be an example of chemical energy or potential energy. In gasoline, there is stored energy that can be converted into kinetic energy. I'm going to go back real quickly because this picture, in theory, actually has both types of energy in it. So this right here is our kinetic energy, and then up here, the water behind the dam would be actually potential energy. Going back here, I mentioned the chemical gasoline having energy. But you can also argue, okay, right here, this guy's stomach, belly, storage of fat. That's another example of potential energy. So kind of want you to get those concepts. All right, and then also on this section, we want you to realize there are laws of thermodynamics. Again, this is not biology stuff, it's borrowed from physics. And there are actually 3 different laws, but for biology, we're real concerned only with the first 2. So that's what we're gonna learn. And I want you to know these. So the first law of thermodynamics is energy can be transferred or transformed, but it cannot be created or destroyed. So what we're doing is we can go from kinetic to potential to kinetic, back and forth, but it's not being created or destroyed, it's just being exchanged. So here we see the gasoline being put in the car. That is a potential energy. And then here we see that we're using that gasoline to push this car down the road, and that would be an example of kinetic energy. And this car should be condemned with all the smoke that's pushing off. And the gasoline is only so efficient, probably only about anywhere from maybe high 20s to low 40% of that is being used to push this car down the road. I'm actually, with all the smog coming out here, I'm guessing it's closer to 20. All right, let's move on to the second law of thermodynamics. Is for every energy transfer or transformation, it increases the entropy of the universe. Which means it's entropy is another word for disorder. So every time we transfer energy, it becomes a little bit more disorganized. And some of that energy then is released as unusable energy in the form of heat. And so I'd like to go back here and describe that again. So what's happening is let's say if under good condition it is 40%. It's probably what actually let's use 20 on this one. This is terrible. This car should be, hopefully it's not on the road anymore. But 20%, that means 80% of that energy is being transferred at heat. And if you think about how cars are built, we have coolant systems, we have radiators and those kinds of things. And that is to deal with the fact that during these transfers that heat is put out. Growing up, actually in the 70s and 80s, one of the most common cars you'd see on the road on fire were Volkswagen Beetles. And because they were air cooled, there was no radiator system in them. It had a rear engine. And the idea behind the design is that as you drove down the road, air would blow across that engine and keep it cool. But if you can imagine in Los Angeles in the summer, August, at 5:30, the cars aren't moving that fast. So as you're driving down the freeway or sitting on the freeway with your car running, Volkswagens tended to heat up, and actually often they would catch on fire. They also had a bad design. They had the fuel line actually go up and over the engine, which I own one. So if you owned a Volkswagen Beetle, you also owned a fire extinguisher. But anyway, so I want you to know the two laws. And again, entropy means disorder. And we'll stop the recording.